This video will cover section 6.5, prime numbers. Okay, so it's going to be relatively quick because you should know what a prime number is. So if not, I will remind you. We're going to start off right off with a definition. So we have something called the divisor of a natural number. Remember that the natural numbers are the numbers that start with 1, and then they just go up in whole numbers from there, okay, up to infinity. So a natural number A is pretty much a factor. That's what we've kind of taught you it's called in school of another natural number b, provided that there exists another number j, also natural, such that a times j equals b. So for example, the number 10 is the same as 5 times 2, okay, where 5 could be my a, 2 could be the j, and 10 is equal to that natural number b, okay? So we're going to jump right into some examples here on what we're going to be doing this unit. Determine all of the natural number divisors of each number. So we want to find all the factors that go into these numbers. So we're going to start with letter A, which is 9. You always want to start with 1 because 1 times the same number is 9, okay? And then you just work your way up from there. 2 does not go in there, so I can't put that one, but 3 does. 3 times 3 would be my 9. Now here you don't have to write it 2 times, you can, it's really up to you. But these would be all of my divisors for 9. Moving on to letter B, 11. If you don't know already, 11 is only equal to 1 times itself, which would be 1 times 1 and 11. So this one only has 2 divisors. Okay. Moving on, letter C, 24. So 24 has quite a few. Again, we're going to start with 1. So we have 1 times 24. We also know that 2 times something is 24. 2 times 12 is 24. 3 times something is also 24. 3 times 8. And 4 times 6 is also 24. And if you see here how I kind of did it backwards, you don't have to do this part anymore. So 5 doesn't go in, 6 goes in, we already have it there. Okay, so this would be the list of divisors for 24 or factors of 24. Relatively simple. Let's go ahead and define officially now what a prime number and a composite number is. So that number 11 that we only had one in itself, we know that's a prime number, and here's why. A prime number is a natural number greater than 1 that has exactly 2 factors or divisors, and those divisors are itself and 1. So that's the main thing here, itself and 1. Notice for there's always a little bit confusion on this because 2 is actually a prime number even though it's an even number, okay, because most people associate even numbers with having divisors, 2 is only equal to 2 times 1. So therefore, 2 is also a prime number, okay? A composite number is the opposite. So if it has divisors that are in addition to 1 and itself, then it's composite, okay? So we're going to just do a few examples. I'm going to make these up right on the spot. Let's say we have 54, okay? Well, I just read off just by looking at this, since this ends with a 4, I know that this is an even number, okay? And even numbers are always divisible by 2 because that's just how we know it. That's how we've learned it to be, okay? You can keep dividing this by 2, and you'll end up with a bunch of factors. So this would be a composite number, okay? What about 17? So if you're not sure, you start trying to come up with the factors. I know 1 times 17 is 17. 2 is not going to go in. 3 is not going to go in. 4, 5, 6. It looks like none of them are going to work. It's just 1 and 17. So this one is going to be prime. Okay. What about, let's say we have a really big number. So let's say 3,147. I don't know. I'm just making this up. If we don't know, then we have to try to divide this, okay? And we could do that. We can say, well, I can try to divide it by 2. 2 is not going to work because you see how it ends with the 7. So right off the bat, I know it's not an even number. It's not going to be divisible by 2. We can try 3. We can try let's try 3. So 3147 divided by 3. And you want it to go in evenly. So let's see. I'm going to do this really quick. So 14, 3 into 14 is 4. That's 12, 27. 3 goes into 27 9 times. Wow. I totally guessed at that. But it looks like 3 times 1049 is going to work, which means that this has more factors besides 1 and 3147, if that makes any sense, because these two guys are factors. So that means, or divisors, that means that this one is also going to be composites. Okay, but what if this hadn't worked? What if this had like a remainder or something? Well, we'd have to try another number. We'd have to try 7, maybe 9, maybe 6, maybe 8. We'd have to keep going. So because of that, I have something else to show you. Here is a table of divisibility tests that you can do so you don't have to do so much work. Okay, obviously, if you have a calculator, you can just kind of keep plugging numbers in and checking. But these are kind of cool because they give you tricks, so to speak, on how to tell if something is divisible by one of these numbers. Okay, I'm not going to go through all of them because there's quite a few. Some of them are self-explanatory. For instance, 2, if it's an even number, we already talked about that. 4 is similar to this one. This one has to do with the last, I believe, 2 digits. So if the last 2 digits are divisible by 4, then the whole number is divisible by 4. Okay. 5 is if it ends with a 0 or a 5, which is, 5, 10, 15, 20, pretty self-explanatory. 10 is if it goes in 10, so it has to end with a 0. We're going to go over some of the ones I did not point at. 11 is kind of cool if you want to take a look at it. I highly recommend it. I'm not going to go over this one, but if it's a neat trick. By the way, this chart is also in your book, okay? So we're going to go ahead and look at some of the divisibility tests here, okay? So here's the rule for the number 3. If you add the digits of the number and that number is divisible by 3, then that means that the entire number is divisible by 3. So we have an example here. I'm going to go ahead and actually just do an example so we can kind of see how this works. Okay, so let's say you have the number, and we'll start with something that's that we know is divisible by 3. Okay, so let's do 99, for instance. Okay, well, if you add the numbers, we have 9 plus 9. And 9 plus 9 is 18. And 18 divided by 3 is 6 with no remainder. So 99 is divisible by 3. Okay, let's try something bigger. So let's do, I'm just going to make it up, 1749. Okay, so if I'm going to add the numbers, it'd be 1 plus 7 plus 4 plus 9. So that would be, let's see, 1 plus 7 is 8, plus 4 is 12. 12 plus 9 is 21. And can we divide 21 by 3? Yep, we get 7, which is a whole number, a natural number, so that is also going to work. So that means 1749 is also divisible by 3. Okay, well, I'm going to try one that's not going to work just so you can see how it works. Let's say we have 85. Okay, so that would be 8 plus 5, and 8 plus 5 is 13. Can we divide 13 by 3? Well, we can, but we're going to get a decimal. Okay, it's going to be 4 and 1/3 or 4.33. So that means that this one is not divisible by 3. And that's how these work. Okay, let's take a look at 6 because that's the next one. It says 6 is going to work if the number is both divisible by 2. So that means that it has to be even. So it has to be an even number and has to be divisible by 3. Okay, so for this one, let's see. I don't think I wrote any examples. Let's go ahead and just come up with one. So let's say we have, and this might not work. I don't know. We'll see. 863. Oh, that's not going to work. 64. Okay. Well, I mean, it's even because of the 4. It ends with the 4, so it is even. Okay, so now we're going to see if it's divisible by 3. So for that, I need to add 8 plus 6 plus 4, which would be, let's see, 8 plus 6 is 14. 14 plus 4 is 18. And is that divisible by 3? I believe it is because that comes out with a natural number. So that means that 864 is divisible by 6. Okay? And that's how this one works. I'm gonna go ahead and move on. I don't want to take too much time on these. I have a few more to show you. Then I'm gonna just show you the last part of this section. And that'll be it. Okay, so we have divisibility by eights. This one says that the last 3 digits of the number have to form a number that is divisible by 8. So all we have to look at are the last 3 numbers of the entire number. So for an example for this one, okay, let's say we had 4368. Okay, so if I'm only going to look at the last 3, that would be these 3 right here. Now, obviously, that's still kind of a lot of work, but it's easier to divide 368 by 8 than it is to divide an extra number. So let's see, 8 goes into 36 4 times. It's going to give me 4, 8. 8 goes into 48 6 times. So it looks like it is divisible. Remember, as long as it ends in a whole number, a natural number, it's going to work. So that means that 4368 is indeed divisible by 8. Okay, interesting. Last one here, just so we can see how this one works. This is kind of a cool one. Divisibility by 9 is another addition one. So what you do is you add up all the numbers, and if that number is divisible by 9, then the whole thing is divisible by 9. So it's kind of like the threes, okay? But now it's divided by 9. So let's just try one. Let's just make up a number here. Let's do 2, 1, 4, 3, 2. I'm just making this up, okay? So this would be 2 plus 1 plus 4 plus 3 plus 2. So let's see, 2 plus 1 is 3, plus 4 is 7, plus 3 is 10, plus 2 is 12. Is 12 divisible by 9? Well, not if it is you're going to have a decimal, so no. So that means that this number is not going to be divisible by 9. Okay, let's try another one. Let's try 1, 2, 3, 4, 5, 6, 7, 8, 9. Just for the fun of it. Let's see. So I'm going to add these as they go. So 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15, plus 6 is 21, plus 7 is 28, plus 8 is going to be 36, plus 9 is 45. And 45 is divisible by 9. It gives me 5. This is actually pretty interesting. I recommend if you have any free time to look something up on this regard because there's actually a really neat pattern that goes with the nines and with this pattern here, okay? But anyway, those are the rules of divisibility. Yeah, that's the last one I'm going to show you. So if you want, if you need more help with these, because like I said, I'm not showing all of them to you, by all means, let me know. But the complete list of the rules are in this chart right here, okay? All right, so let's go ahead and finish this up now. I believe there are just 1 or 2 more things to look at. All right, so in this unit, we also see something called the fundamental theorem of arithmetic. This is one of those really big theorems that, is super important. And it's actually very, very basic. It says that every composite number, so remember the number that has multiple divisors besides 1 in itself, can be written as a unique product of prime numbers, disregarding the order of the factors. So that means that I can pretty much factor each one and I will get the same prime factors at the end. So I just went ahead. I'm sure you know how to do this. What I did for this is I just added some examples just to kind of go over. So we can see here that 495 is the number they were factoring. So if you factor this, this is the same as 3 times 165, okay? and 165 is the same as 3 times 55, and 55 is the same as 5 times 11. So if you follow all the primes, we have two threes, so 3 squared, 1 5, so there's the 5, and the 11. So that matches what we have so far. Let's say you didn't know that 3 times 165 was 495, and you went ahead and said, you know what, I'm going to divide by 5 because that's easier because it ends with a 5. Well, you would use this tree over here. So 5 times 99 is also 495. But 99 is 11 times 9, and 9 is 3 times 3. You can see that we still have our two threes right here. So we still have our 3 squared. We still have the 5 and the 11. So regardless of how you factor, as long as you're, factoring correctly, you will get the same prime factorization here. And that's what this theorem is telling us. Okay. Here's another example. I'm not going to really go over it too much, but here's another example with 4004. So you can see they broke it down all the way down to its roots. It has two twos. That's where that 2 square came from. 7, 11, 13 are the other ones. And that's it. Okay. You know that you are done when you can't break these down anymore. So if you get to a number down here, you're not sure if, let's say you didn't know 13 was prime, okay, you would try to divide it by, numbers that are smaller than it to see if there was any more factors. Once you can't factor these anymore, that's because it's a prime number and you've got into all of the primes. So this again is called the prime factorization. And with that in mind, I have one final thing to show you. This is part of one of the, I think, three problems actually you're going to be doing. Um, it's a method of finding primes. So there's actually no formula officially to find the prime numbers. It's something that mathematicians have been trying to figure out for quite a long time. However, there is this method that we can use, within a certain bounded amount of numbers. Because if you did this forever, I mean, you'd be going forever. But it's called the sieve method of finding primes. And what it does is it starts by crossing out all the multiples of, well, it starts with the even numbers first. So we start with k is equal to 2, sort of, okay? But you skip 2 because 2 is a prime, okay? So multiples, or you can even think of it as an even number, multiples of 2 would be all the even numbers. So 4, 6, 8, 10, 12, 14, 16, 18, 20, and so forth. And you just cross them out. So that's what you see here. All of those are crossed out. And essentially, you could cross out basically all of this column, because all of those are multiples of 2, okay? And then once you're done with that, you say, well, let me move on to k equals 3 now. So now we're going to do multiples of 3, but again, excluding 3, because 3 is the actual prime number, okay? So multiples of 3 would be 6. So let me see if I can. So it would actually different color. So it'd be 6, 9, 12, 15, 18, 21, 24, 27, 30, and you get the idea. So you would go again, crossing out all your multiples of 3, and then you would move up to 5, which is the next prime number. So now we're at 5. So that would be your tens, your 15s, your 20s, your 20. And for this one, you can actually see that again, all of these, they're already crossed out, but that would cover all of those. And it would cover all of these because according to our rules of divisibility, anything ending with a 5 or a 0 is divisible by 5. Okay, and so forth. So it goes all the way up to 9, to the point where all you're left with are these blue numbers. Now these blue numbers are the primes. So from 1 through 100, we have all these numbers. Okay, I'm not going to circle them all, but pretty much anything that's blue left over that you didn't cross out, yeah, I guess I can circle them all, that you didn't cross out, that means that it's not divisible by any of those other numbers, which means it's only divisible by 1 and itself. So therefore, the definition of a prime. Okay, so you're going to need this method for a couple of your problems. If you want, you can also look it up online, and I'm sure there's some more explanations if you want, to read more up on it. But yeah, that's about it, guys. So hopefully this was a nice short video, and that you have no problems with the work. Thank you.